two populations. This is material from Chapter 2 of your textbook, and this lecture is courtesy of Dr. Root. So before we move into two populations, I just want to review what we discussed in class on Friday. Okay. So the setup was a test of hypotheses, and there were some elements that we used when we tested a hypothesis. So a hypothesis is a statement of the population average or population mean, which is given by this object, that Greek letter. And the thing that estimates the population mean is the sample mean. So if, for example, if the sample mean is very large from the null hypothesis value at the population mean, then that's evidence of the alternative hypothesis. But if it's pretty close, that's evidence of the null hypothesis. So on the next slide, we're going to use S to denote the standard deviation, and N is the sample size, or the number of observations. So in Chapter 5, we perform this hypothesis test. And when we do a hypothesis test, we need a test statistic. And the test statistic we use is this t statistic. This n-1 is called the degrees of freedom, and that's given right here in the bottom. Okay. And this has a pretty standard form that's familiar with test statistics. That is the estimated value, which is the sample average here, and the population mean or value under the null, divided by the standard error. Okay. So the standard error of the sample is S over root n. So let's just talk about the heuristic here. So the idea here is if x bar is far from the population mean, that is being hypothesized in the null, then this is evidence against the null hypothesis. And this t distribution, it has lower probabilities the further that this goes out from this population mean mu here. Okay, so given our data and our null hypotheses, we compute this test statistic, and we compare it to where it should be, or how likely it is to observe the data, using the theoretical distribution. Okay, and then you'll use statistical software such as R or Python to calculate your p-value. And implicitly, it's using some calculus to calculate the p-value by calculating the area under the curve of a t-distribution. Okay. This corresponds to one of three hypotheses. One is that the null hypothesis value is smaller. The other is that it's larger than some value, or that it's not equal. Now, evidence that it's smaller than some value means that the test statistic would be negative, i.e. it would be to the left here, okay? Evidence that it's greater means that it's positive, and the bigger it is, the less likely it is to be consistent with the null hypothesis, okay? Then under the alternative, there are two ways that this could be false. It could be too large, or it could be too big. Okay. Then we calculate the probability. So for example, in this alternative hypothesis, we calculate the probability it's bigger than the observed value, than the observed test statistic, where the test statistic is given by this quantity. Okay. And when we calculate that probability by calculating the area under this curve, which corresponds to the probability, we're going to get a p-value. So when you're writing up your case studies, a p-value that's really small, like 1% here, that means it would happen about 1 out of 100 times, assuming your null hypothesis is true. So the smaller this p-value is here, the more we get into this convincing region that we're convinced that the alternative is true, okay? Or that we reject the null in favor of the alternative, okay? When the p-value is more moderate, 10%, that's not that infrequent. That's just 1 in 10 times. So when the p-value is about 0.1 or 10%, that's suggestive, but not the most convincing, I would say. Okay, now 0.05, that gets us to the more convincing area. So kind of a moderate level of I guess evidence or how convinced you might be. But the key point here is the smaller this is, the more convinced you are. And in your writing, while this vocabulary of convincing, moderate, suggestive, inconclusive, while that is, relative to each individual, I would like you to use some of this wording, okay? So you have a p-value that's like between greater than 1% but less than 5%. Use something like a moderate. If you have something that's around 10%, say something like inconclusive or suggestive. So I hope that you'll incorporate some of this vocabulary into your case studies and your writing, rather than saying, I reject the null hypotheses at this level of significance, because um, I will start to take off points if you do that. One of the other things that I want to emphasize is I said that this is kind of relative to each individual and even area of study, what people consider convincing or moderate or suggestive. That does depend on area of study and application. So just keep that in mind. The point of this is that p-values are a spectrum, whereas when you say I reject at the 5% level of significance, that is a hard cutoff. And I want you to shift away from the hard cutoff to more of a spectrum. Okay, let's review our data set in which we investigated 15 sets of identical twins where one twin had schizophrenia and the other did not, and we recorded the hippocampus volume. This data set was in the US and Canada. Okay. One other important thing about this data set is that it's a matched pair design. So one would be tempted, and it's up to the discretion of the authors, to what level of inference they want to make. So like what population, what scope of inference would you use? That's up to the authors, and the match pair design helps to kind of extend what you could say about the population, okay? Because it controls for unobserved confounding variables, and it mitigates them, okay? So the schizophrenia data, one important thing to think about that was very subtle was the independence of the data set. So for example, does the unaffected group, does their hippocampus volume affect the non-schizophrenic individuals? Well, the answer is yes, because they're identical twins. One identical twin is, if one identical twin is in the schizophrenic side, well, then the issue is that there could be genetic or other factors such as income that make an individual's hippocampus region um, larger. And that, for example, could be due to um, factors like income or nutrition or a whole variety of things. Okay, so it could also be due to genetics. So because one twin is in group A and the other is in group B, well, it's more than likely the twins are correlated. So the two groups are not independent, and that's important to note. It is only because we take the difference that we account for those two things, and we take the difference with the twins, and now the data is independent. Okay. Okay, so in the schizophrenia data, when we apply our t-test, we need to check for normality. So there's some things to think about when we check for normality. The first is we could do a data visualization. And you see the box plot here on the right. Okay. Um, the question is this normal or not? Okay. So you look at the box plot, the first thing that stands out is that it does look mostly symmetric, but the median is skewed. And because the median is skewed, some people might just say the data is not normally distributed. Okay. And they wouldn't be wrong or they wouldn't be right. But the correct way to think about this is that the null hypothesis is that the data is normally distributed, which happens to be the null hypothesis, something called the Shapiro test. And the Shapiro test tests for normality, where the null is that the data is normal, and the alternative is that the data is not normal. Okay. So when we look at this box plot, you should ask yourself, is it possible that under a normal distribution, that the median could be skewed as much as we observe it? And the answer is probably. Like, it's not convincing that it couldn't be normally distributed. So that's one level of examining normality, is with the graph of the box plot. Another way to look at it would be with the Shapiro test. So when we perform the Shapiro test, it computes the p-value, and it gives us a p-value of 0.11. Now, the p-value of 0.11 is suggestive but inconclusive. So that means that we fail to reject our null hypothesis, and the randomness in the median is due to random chance. So we don't have enough evidence that it's not normally distributed, so we're okay to proceed. The data is normally, assuming that the data is normally distributed according to the Shapiro test and how you interpret the box plot. Now, one other piece of evidence I encourage you to use if you're using a graph is not necessarily the box plot, but typically the standard is what's called a QQ plot. I didn't provide one here, but I'd encourage you to examine it. So typically, when people examine normality, you'll perform the Shapiro-Wilks normality test and examine its p-value. The second piece of evidence you'll examine is a graph. So either a histogram, a box plot, or the best one is the QQ plot. Okay, so that's one of the assumptions of the schizophrenia of our t-test, is that it's normally distributed because our sample size is less than 30, okay, and significantly less than 30. One of the other assumptions that we talked about was the independence. It wasn't independent until we differenced it, but the data is differenced, right? If we look at this, okay, look at how we did it. So that's the second, those are two assumptions that are met, okay? And once we perform our test statistic, we calculate our test statistic that gives us this t-value, and it gives us this p-value of 0.006. That's less than 1%, and I would say that's very convincing evidence of the alternative hypothesis, which means that the mean hippocampus volume of schizophrenics is not equal to the mean hippocampus volume of non-schizophrenics. So there is a difference. And there's other important information. The 95% confidence interval estimates this difference to be as small as 0.066 cubic centimeters or as much as 0.33 cubic centimeters. And the average is 0.19. So it'll tell us by how much as well. So there's lots of good pieces of information here. Okay. So something that we discussed last time in detail was in hypothesis testing, we have all these different outcomes here. So when the reality is that the null hypothesis is true, we can make the correct decision and conclude that the null hypothesis is true or fail to reject it, or we could go with the alternative and make what's called a type 1 error. Okay. Now a type 2 error means that we fail to reject the null, i.e. decide the null is true, when the reality is that the alternative is true. The probability of a type 1 error is related to something called power via this relationship. And high power is really good. Okay. It means that you're able to reject the null hypothesis correctly when the alternative is true. Now, paired t-tests have higher power because the pairing reduces the variation. Okay, so in addition to our conclusion, we can be pretty confident in our statistical methodology. Okay. Okay, now one other piece of output that was produced was something called the confidence interval. Okay, and I want to go through a few details of it. So how do we calculate our confidence interval? Well, we take our estimated value and add or subtract the standard error. Okay, so one thing that you have to be thoughtful of is, do you want how much confidence do you want? So confidence relates to this type of alternative hypothesis, and it produces the interval that corresponds to, for example, 95% of the area being between these two values. It doesn't have to be 95%, it could be 90%, it could be 99%, it could be any number, typically greater than 90%. So that means there's a 5% chance. So if it's 90%, it means there's a 5% chance that it's bigger, a 5% chance that it's smaller. If it's 95%, it's 2.5% that it has this value or bigger than the upper value of the confidence interval, and a 2.5% chance that it has the value less than the confidence interval. Okay, so if we wanted to calculate what this range would be, we can do this with the confidence interval. And those are the typical levels of confidence, just FYI. Okay, here's another graph of the same thing. So the alpha is your level of significance. So for example, you want a 10% level of significance. This would be a 90% confidence interval, 5% in each tail. So 10 divided by 2 is 5%. Okay. We'll discuss this later, but this is a little experiment that we might do in class. Okay. Okay, if we want to compare two populations, it's important to keep straight the null and the alternative hypotheses. There are two alternative hypotheses. The null is always a statement of equality. The alternative is that one value is bigger than the other, or that they're not equal. Okay, and how we'd calculate this is there's two different scenarios to consider. The typical case is to assume they have the same variance and calculate what's called the pooled standard deviation for population 1 and population 2. After all, we want to know if the mean of population 1 is equal to mean of population 2. Okay, so we would pool the variance to estimate it. If you can pool the variance, you should always do it because it leads to a more powerful test. If you can't, then you should not pool the standard deviation, of course. Okay. If you can pool it, this would be your test statistic. Okay. So notice under the null hypothesis, this piece right here, the mean of population 1 minus the mean of population 2, that goes away. And if our alternative is that the mean of population 1 is bigger than the mean of population 2, then this test statistic should be positive and large. So the further away the sample average, the thing that estimates the population mean of population 1, the further it is from the estimate of population 2's mean, the more unlikely it is to observe your data. Okay, this t-distribution will have degrees of freedom given by this. Okay. Okay. Just like, so with this test statistic, we can calculate the p-value using the t-distribution, just like we did with a single population mean. But we can also calculate the confidence interval using that distribution. And if we can pool the variance, the confidence interval is given by this formula, the estimated difference plus or minus some form of the standard error. Okay, and in this case, this is the form of the standard error. Okay, so now I want to talk about what's called Darwin's Finch data. So remember that pooling the variance, that's the most powerful test, but we have to make sure that that's appropriate. Okay, so we have a test called Levene's test. And Levene's test is that the variance of the two populations are equal. The alternative is that the variance of the two populations are not equal. So Levene's test allows us to assess this assumption. Two alternative things that you can do is to use a box plot or to look at a histogram. So the typical standard is to do a visualization, whether it's a box plot or a histogram. I have a slight preference for box plots, but you can do histograms if you prefer. And look at the variance to see if the spread of the data is about the same in your visualization. Okay. And it's also to compute the p-value, Levene's test. Now, I'd just say that it's not always a perfect test, whether you're doing box plots or p-value. So it's important to do both, okay? And if they agree, then that's really helpful. Okay. Now, there's another scenario, which is that the two populations just don't have the same variation or standard deviation. Same thing, okay? And if they have different variances, your test statistic is calculated in this way. The only thing that's different here is the variation, how you calculate the variation of the difference, okay? is given by this formula when you cannot pool it. This simplifies, of course, under the null hypothesis to just this statistic, and a large value of the t-statistic indicates that the mean of population 1 is bigger than population 2, indicating the alternative is true. Okay. Now, the degrees of freedom is a lot harder to calculate. It's given by this formula. But fortunately, the two things are true. One is written down for us in the textbook. Two, it's built into the commands. So, you don't have to compute this by hand. Okay. One thing to note is that the degrees of freedom will be smaller if you pool the variances, which means that your test will be less powerful. So I think that this is switched. So degrees of freedom will be smaller if you had not pooled the variances. Okay, so it's better to pool it, and that's the general case. Okay. If in fact you can't pool your test, though, you should not pool it because that'd be the wrong thing to do, and you wouldn't actually get that power. Okay. Okay, so there are assumptions just like there were for a single population. Okay, and the assumptions here for comparing two populations are that the data are obtained from a random sample of the population. The data sampled are independent, okay, of each population. Someone in group 1 doesn't affect someone in group 2, okay? The data is normally distributed, or the sample sizes is 30 or bigger in each group, okay? If it's not bigger than 30, you need to inspect it with a histogram or box plot or Shapiro test. Okay. So some things that you can do to assess these assumptions, you can look at the box plot. Box plots tell you normality and equal variance. Histograms, same thing. QQ plots just assess normality. Shapiro tests only assess normality. Levene's test only assesses variance of the two populations if they're equal. So the null hypothesis is that the variances are equal. And independence, you have to assess that by analyzing the sample method or knowledge of the data. So that is perhaps the most subjective in some cases, and that is independence is the one that cannot be assessed by a graph or a p-value.